Well, this project is about the Laval nozzle, which is an important part of the rocket engine. The purpose of this study is to explain how the nozzle works using compressible flow principles. We studied how the gas moves through the converging section, the trough, and the diverging section, where its speed changes from subsonic to supersonic. And we also explained how the pressure affects the performance of the nozzle in different operating conditions.
Assalamualaikum and hello everyone. My name is Mama Afzal. So for our fluid mechanics 2 group assignment, the first thing I did is do the introduction part. Within the introduction part, we talk about the rocket engines and the main component behind it being the converging-diverging nozzle. Then we go into further details on how the converging-diverging nozzle works, the mechanics behind it, and how it relates with our fluid mechanics 2 topic, compression flow, how the relationship works between the nozzle cross-sectional area, pressure, and the velocity entering and exiting the nozzle. We also lay out the objective for our reports. For the second part, I did the nozzle geometry and the working principle. For this part, we go into detail the main different section within the nozzle, which consists of 5 different sections, being the combustion chamber, converging section, the throat, diverging section, and the exit. So for this part, we goes into what happened within each section and show the progress on how it start from combustion and essentially creating thrust for the rocket to propel into space. Thank you.
Next, I will present about the compressible flow principles. Compressible flow is a fundamental concept in the operation of a rocket engine converging-diverging nozzle. In such a nozzle, the gas density changes significantly due to variations in pressure and temperature as the gas accelerates from the combustion chamber to the nozzle exit. So the first part of the compressible flow principles is the speed of sound. The speed of sound is given by the formula C equal to square root KRT. C is the speed of sound, K is the ratio of specific heats, R is the specific gas constant, and T is the absolute temperature. In a rocket nozzle, the combustion gases in the chamber are at very high temperatures, resulting in a high speed of sound as the gases expand through the nozzle. Their temperature decreases, causing the local speed of sound to decrease. The next part is the mesh number. The mesh number is the ratio of the local fluid velocity to the local speed of sound. It is one of the most important parameters in compressible flow because it determines the flow regime. The mesh number is defined as M equal to V over A. The flow regime based on mesh number are explained below. If the mesh number less than 1, it is subsonic flow. If the mesh number equals to 1, it is sonic flow. Meanwhile, if the mesh number is more than 1, it is supersonic flow. Thus, the mesh number describes how the gas velocity changes throughout the nozzle and explains the transition from subsonic to supersonic flow. The next part is the compressibility effects. Compressibility effects occur when the density of a fluid changes significantly due to change in pressure and temperature. These effects become important when the mesh number is greater than approximately 0.3. In incompressible flow, the fluid density is assumed constant. The main compressibility effects in a converging-diverging nozzle are: the first, pressure decrease. As the gas expands through the nozzle, the pressure decreases from the combustion chamber to the exit. Second is the temperature decrease. The expansion process converts thermal energy into kinetic energy, reducing the gas temperature. Third is the density decrease. Lower pressure and temperature cause the gas density to decrease during expansion. And fourth is the velocity increase. The reduction in pressure energy and thermal energy results in a significant increase in gas velocity. The last part is the stagnation and static properties. In incompressible flow, static properties are the actual properties of the moving fluid at a given point. While stagnation properties are the properties of the fluid would attain if it were brought to rest isentropically without heat transfer or friction. There are 6 properties, that is the static pressure and stagnation pressure. static temperature and stagnation temperature, and also the static density and stagnation density. For an isentropic flow, the stagnation temperature is related to the static temperature by the formula T0 equal to T plus V square over 2Cp. The relationship between stagnation and static properties can also be expressed using the mesh number, that is using the three formula below. In a rocket nozzle, the stagnation properties are highest in the combustion chamber, where the gas velocity is relatively low. As the gas accelerates through the nozzle, the static pressure and static temperature decrease while the velocity increase.
Good day everyone. So moving on to the next one, isentropic flow relations. So actually the flow through the ideal portion of the nozzle is commonly assumed to be the steady, adiabatic or maybe reversible. But therefore, the flow is considered isentropic, meaning that the isentropy remains constant. So the main isentropic flow relations describe that the relationship between the Mach number and the static pressure, temperature and also the density of the gas. So actually when the Mach number increased, the static properties decreased. So this is especially important in the diverging section of the nozzle, where the flow accelerates from the sonic to supersonic speeds. Next we have choke flow. So actually choke flow occurs when the Mach number reaches on one of the throat of converging-diverging nozzle. So the throat is the section with the minimum cross-sectional area. As the back pressure decreased, the mass flow rate increased until the flow reaches sonic condition at the throat. So at this point, the flow becomes choke. And further reductions in downstream pressure do not significantly increase in the mass flow rate. So this is very important in rocket engines because the choke throats control the maximum mass flow rate through the nozzle. So since the flow at the throat is sonic, pressure disturbance from downstream cannot travel upstream and influence the flow. So the next one we have the critical pressure ratio. So actually it determines when the choking occurs. So for an ideal gas, the ratio depends on the specific heat ratio, or we call it as gamma. So for air, the gamma is equal to 1.4 and the critical pressure ratio is approximately 0.528. So therefore, when the downstream pressure is sufficiently low and this critical condition is reached, the flow becomes choke. So the area Mach number relationship is also important because it explains how changes in nozzle area affect the flow velocity and the Mach number.
Hi everyone, I will talk about how the flow behaves inside the nozzle. The nozzle has two parts, converging and diverging part. In the converging part, the pipe gets narrower. Here, the gas is still slower than the speed of sound. We call this subsonic. As the area gets smaller, the gas speeds up and the pressure, temperature and density will drop. At the narrowest point, called the throat, the gas reaches exactly the speed of sound, which is Mach number 1, or choke flow. Once this happens, the flow rate through the nozzle becomes fixed. After the throat, the pipe gets wider again. This is the diverging part. Here, the gas is now supersonic, faster than sound. Interestingly, in this part, making the area bigger actually makes the gas go even faster. Overall, the nozzle turns the gas heat energy into speed. That's how rockets get their thrust.
Hello and good day everyone. Today I will be presenting about rocket nozzle exit condition and their impact on thrust performance. The performance of a rocket nozzle is primarily driven by the relationship between exit pressure, PE, and ambient pressure, PA. Depending on this ratio, a nozzle operates in one of three modes, which is perfectly expanded, under-expanded, or over-expanded. First, in a perfectly expanded nozzle, exit pressure matches ambient pressure, which is PE into PA. The flow exits smoothly with zero shock disturbance, achieving maximum thrust efficiency. However, this ideal condition only occurs at a specific design altitude. Second, in an under-expanded nozzle, exit pressure is higher than ambient pressure. The gas continues expanding outward beyond the exit, forming short diamond in the exhaust pump. This occurs at high altitude, and while thrust efficiency remains high, a small amount of thermal energy is lost in lateral expansion. Next, we have the overexpanded nozzle condition. This occurs when the exit pressure is lower than ambient pressure. The higher external pressure compresses the exhaust jet inward and shock wave may form inside the nozzle or at the exit, reducing thrust. In several cases, flow separation occurs, causing unstable thrust and mechanical vibration known as side loads. This condition is most common at low altitude, such as sea level launch. When a nozzle is significantly overexpanded, the flow adjusts to the higher ambient pressure through a shock wave. A normal shock may form inside a diverging section, causing a sudden drop from a supersonic to subsonic flow with a large pressure and temperature rise. Alternatively, oblique shock at the exit are less severe, while expansion wave help the flow turn outward. For a practical nozzle design, engineer must make trade-off since rocket operate from sea level to vacuum. At sea level, nozzles are slightly overexpanded to avoid flow separation and structural damage. At high altitude, the nozzle become underexpanded, but this is acceptable since thrust loss is minimal. Finally, advanced concepts like aerospike and dual-bell nozzle are being developed to maintain near optimal expansion across all altitude, solving the overexpansion problem entirely. That's all for me. Thank you.
I will continue my part, which is the important equation that I can relate with the converging and diverging nozzle. After I do research and my study, the equation that I can use is first the Mach number, speed of sound, isentropic relations, area Mach number relations, critical pressure ratio, and the mass flow rate. The engineering application parts, after I did my research, most of the information that I got is from the National Aeronautics and Space Administration, which is NASA. So first application that I can relate, which is the launch vehicle. Converging diverging nozzle are commonly found on a launch vehicle because it helps accelerate hot combustion gases to extremely high speeds. Then I also figure out which is the satellite thrusters. Satellite thrusters use small converging diverging nozzles to provide precise and controlled thrust for attitude adjustment, orbital correction, and station keeping.
In conclusion, the Laval nozzle is a very important part of a rocket engine because it converts heat into thrust. The gas accelerates from subsonic to supersonic speed as it passes through the nozzle. We also learned that the relationship between the exit pressure and the ambient pressure affects the nozzle performance. Overall, this project shows how the concept of fluid mechanics too are applied in real rocket propulsion systems.